Hello everyone, here we are going to start looking at the summer practice exam 4A. And we're going to start with this question about which species is an oxidizing reagent in this given reaction. And so we know that the oxidizing agent is what gets reduced. And so to figure that out, we're going to have to keep track of how our electrons are changing. And our counting system for that is oxidation numbers. And we know that our oxidation numbers need to add up to the overall charge on the molecule. When we have something like Cl2, we have something that's on its own, it's neutral. The oxidation state is going to be 0 for each of those fluorines. Then we have sodium bromide. And if we look at our list of suggested oxidation numbers, sodium is an alkali metal, bromide is a halogen. We're going to assign the alkali metal first. Give that its -1. Which works out, or I'm sorry, +1, silly me, +1, which works out so the bromide can have its preferred oxidation number of -1. And then we can see that those oxidation numbers add up to equal the overall charge in the salt, which is 0. And then we can assign, on the right, the sodium chloride very similarly. We assign the alkali metal with its preferred +1 first. The chloride has to be -1. And then the Br2 is going to be 0. And so then we're going to look and see what changes. And we can see that the chlorine changes. It goes from 0 to +1. So that must be gaining an electron, it's becoming more negative. So that means it is getting reduced. And so that means that this is going to be our oxidizing agent. And so the answer here is going to be B, because B is our reactant that is getting reduced. Here in question number 2, we're looking for a redox reaction, or what's true about a redox reaction that is spontaneous in the forward direction for some given conditions. And so when I see the word spontaneous, I know that that's going to correspond to a negative delta G or to a positive cell potential. And then it also says in the forward direction, and I know that for a reaction to proceed in the forward direction, my Q must be less than my KEQ. So I haven't made enough products yet, so I have a smaller Q value because my numerator is smaller. And so then if I kind of take note of just some of the things I know about this given kind of setup, then I can start evaluating the answer choices. We want to see that when it says is consistent, that's like saying is true. And so here for A, it says Q is greater than KEQ. And that's not going to be right because that would mean we have extra products and would instead go in the reverse reaction. So that's out. B says when E cell is greater than 0, which is a way of saying positive. And that matches with our prediction, so that seems like a viable answer choice, but let's look at the other ones just to be sure. Here we can see we have delta G greater than 0, so positive delta G. And that would correspond to a non-spontaneous reaction. That's out. And here in D, they say when delta H is positive, and delta S is negative. This is a little bit of a throwback, but we can still use our thermal thought process to answer this question, where we have our favorite equation, delta G equals delta H minus T delta S. So maybe you can remember that when delta H is positive, endothermic, unfavorable, and when delta S is negative, also unfavorable, this delta G is always going to end up being positive. Always going to be greater than 0 because we're just adding a number to a number, both positive. And so this is out. And then KEQ being greater than 1, we can really only think about this under standard conditions. And since they don't specify standard conditions here, we can rule that one out and settle with B. Okay, in this third question, they've given us a bunch of substances and they want us to figure out what is the best reducing agent under standard conditions. And so we know that the reducing agent is what gets oxidized. When you're oxidized, you lose electrons. And so what I've done here is just started to write out the reactions to a certain extent about what would happen if we lose electrons. And so for the platinum, we're going to end up then actually losing 2 electrons to make PT2+. And then it has a potential equal to negative 1.20 volts. So to figure out this negative 1.20 volts, I looked on the data sheet for where platinum 2+ was being reduced and flipped the reaction to get the oxidation instead of the platinum metal. And so then I had to flip the sign on this potential. And so then we can think about H2 as losing some electrons. It ends up it's going to be 2 electrons. Since we make H+ ions, we'll make 2 of them. And that's going to have a standard potential of 0 volts. This is our She. This is our standard hydrogen electrode. It's our reference point, so we call this 0. And so then if we look at our Cl2, we could think of it maybe as, maybe it's going to lose 2 electrons and make Cl, 2 moles of Cl+. That doesn't feel right, does it? Chlorine doesn't really like to lose electrons, right? It likes to gobble up an electron and fill its octet. And so this reaction just isn't going to happen. And so I'm going to rule it out. And you won't find a reaction like that on the data sheet either. So then, if I'm looking at sodium, I can think about it losing an electron and becoming Na2. Ooh, that doesn't feel right either, does it? Because sodium's not going to lose another electron. As Na+, it has its octet. We'd have to break into core electrons to remove another electron, so this isn't going to happen, and you won't find it on the data sheet either. Okay. And then here we have iron 2+. You think about it losing an electron and becoming iron 3+. And that reaction you can find on the data sheet. And its potential is going to be negative 0.771 volts. Okay. So now we know what's going on with each of these things. And if we're looking for the best of something, what we want to look for is the most positive. And so it seems a little strange, but the most positive one on here is going to be the one that's 0. It's going to be this hydrogen, because it has the least negative half reaction potential. So our best reducing agent here is the H2. Now to number 4, we again have to kind of remember that enthalpy and entropy exist. And they tell us that both of these are positive. So they want us to determine which of the following statements is true. So let's just kind of figure out what's going on with delta G when delta H and delta S are both positive. And so if we were to graph this out, if we have a positive delta H, our line is going to start with an intercept that is above 0. And then we're going to be subtracting off a positive number that gets bigger and bigger as temperature increases. And so this is where we end up with a line like this. Ooh, sorry, got a little curvy, but you get the idea. And so what we can see here is that after this temperature, whatever it may be, now we're spontaneous. And so what we see is that our reaction becomes spontaneous at high temperatures. And so that's like saying our cell potential is going to be more positive at high temperatures, because a positive cell potential is spontaneous. And again, we're looking for what's true. You can go ahead and look at this. So here it says E cell will increase with an increase in temperature. Seems to kind of match what we were saying. Let's read the rest of them. B, E cell will decrease with an increase in temperature. And that's not true. We see delta G decreases, but delta G and E end up having opposite signs of each other. Maybe false. E cell will not change when the temperature increases. And you know, that's not going to be true. Right? We know temperature changes how reactions proceed. Here it says delta G is positive for all temperatures. And that's not going to be true either, right? We can see this crossover point here. And then E says the cell potential is going to be positive for all temperatures. And that's not true, because below whatever this temperature is, this is going to be non-spontaneous. And we'd have a negative E cell in that region. That just helps reaffirm that A is the correct answer. Okay. Here in number 5, we're asking how much work this given reaction can do. And so it can be a little bit intimidating when they're asking you for a number in your answers, but they haven't provided you with any numbers. And when that happens, just remember you have the data sheet to help you out. And so what we're going to have to do is start by determining what our standard cell potential is going to be using this equation here. We're going to figure out what our half cell potentials are. And then once we know what our standard cell potential is, we can plug this in to our delta G equals NFE equation. So let's go ahead and assign oxidation numbers to our reaction so we know what's changing. So this is really easy because just our neutral metals will be 0, and then the others will be the charges. And so we can see that the chromium is going from 0 to +3. It must be losing electrons, getting oxidized. We can write that half reaction here. And it's nice they actually already balanced it for us, so we can keep those along. And we can see that since it is balanced, we're going to have 6 electrons exchanged because each chromium is losing 3. And we have 2 chromiums. So we're going to have 2 times 3 electrons being exchanged. And then we can see our lead is going from 2+ to 0. So it's being reduced and gaining electrons. We're going to have 3 lead ions. Each one of those lead ions is gaining 2 electrons, and we have 3. So again, we have 6 electrons being exchanged, which makes sense because they already balanced it for us. So they should match between our 2 half reactions. And so now we need to get the potentials for these reactions from the data sheet. I'm going to start with the lead because this is our reduction, and we can just get it directly from the table. So this is going to be that negative 0.126 volts. And then for the oxidation of chromium, I'm going to find the chromium reduction half reaction. And then when I find it, it's negative 0.74. But that's for the reduction of the ions, and instead I have the oxidation of the metal. And so I'm going to flip the sign from the data sheet, and it's going to be positive 0.74 volts. And then by just adding those two together, I will get my overall cell potential to be positive 0.614 volts. So now that's what I'm going to use up here in this equation. And so in this equation, we need to know the N, and the N is the number of electrons transferred. And so for this reaction, it's going to be 6. Okay. And then F is a constant. It is how much charge a mole of electrons has. And this number is on the data sheet. And so we can go ahead and calculate our delta G, which will be negative 6 moles of electrons times Faraday's constant then times our cell potential, which is positive 0.614 volts. And what I end up getting is negative 355,450. And of course, we're not just going to leave this like that, right? We need to know what units we have. And it turns out here we have joules. And so we can just simplify this and say our delta G is going to be negative 355-ish kilojoules. And so they're asking how much work this can do, and so we'll just go ahead and say it can do 355 kilojoules. Okay. So a little bit of combining what we looked at for the previous exam, or I guess 2 exams ago, with our new material. And we continue our redox adventure here when we're looking at this expensive voltaic cell. And it's written here in standard cell notation. And so what that means is that this left portion is referring to the anode, and the right portion is referring to the cathode. So we're trying to figure out the cell potential for this under these conditions. And when I look, our concentrations are not 1 molar. So that tells me we're going to have to do the whole Nernst equation, where we figure out our standard cell potential using the data sheet, and then we adjust for not being at standard conditions. Okay. So let's go ahead and convert this into an equation. Actually, let's do it down here, into a full reaction rather than our cell notation. So we know the first part corresponds to the oxidation, so the loss of electrons. And we can see that because we go from neutral PT to PT2+, We must have lost 2 electrons. And then now we can write our reduction half reaction. We can see that we have gold ions that would be gaining 1 electron then to make solid gold. So we have the half reactions. We do need to balance them in order to cancel out the electrons. And so right now we're not balanced. We have 2 electrons being given off, but only 1 electron accepted. And so we're going to have to multiply this bottom half reaction by 2. And now we can see that our electrons would cancel when we combine our half reactions, which is always the goal. Okay, so at this stage now we know what half reactions are happening. We know that we're going to need our standard cell potential, and so we can use the data sheet to figure out what those potentials are. So again, I'm going to start with the reduction half reaction because then I can just get it directly from the table. And I can see that for the reduction of gold ions, it ends up being positive 1.69 volts. And then what I can find on the data sheet is the reduction of the PT2+ ions. And when I find that on the data sheet it's positive, but I'm looking at the reverse reaction, I'm looking at the oxidation of platinum solid here, so I'm going to flip the sign. It will be negative 1.20, maybe. Come on. And it will be negative 1.20 volts. And so then I can just go ahead and combine these 2 reactions and combine their potentials, and I'll get my overall reaction and my overall cell potential. So when I do that, my electrons cancel, as I mentioned, and I'll have my 2 gold ions reacting with my 1 PT solid. To make 2 solid golds and our platinum ions. Okay, and so then our overall cell potential will end up being 0.49 volts. So should we circle B, or I'm sorry, should we circle C and be done with it? No, we're not done yet. All we've found is this first part. Oops. We need to figure out now what N and Q are so that we can figure out our non-standard cell potential. Okay, so one of the reasons why we took the time to figure out what our overall equation is here is so that now we can figure out what Q is. You'll remember that we can write Q the same way that we write equilibrium expressions, but we're going to plug in any kind of concentrations into Q. So we can go ahead and say that our Q expression here is going to be our aqueous or gaseous products. We'll have our platinum 2 plus ions to the power of their coefficient, so just 1 here, divided by any aqueous or gaseous reactants, which will just be our gold ions, to the power of their coefficients. This will be squared. So when we plug in to this, we'll have just 5 molar divided by 2 times 10 to the negative 5 molar squared. And so when we solve that, we find that our Q is pretty big. It's 1.25 times 10 to the 10th. Okay, so let's go ahead and plug into this equation. The last thing we need in order to be able to plug into that equation is what the value of N is. And we can see from our half reactions and what we had to do to cancel out our electrons that we ended up having 2 electrons transferred. So our non-standard cell potential is going to be equal to our standard cell potential, which is 0.49 volts, minus 0.0592 divided by N, which is 2, times the log of Q, which is 1.25 times 10 to the 10th. And when we plug this in carefully into our calculator, we end up finding that this is 0.191 volts. And so then our answer choice does end up being B. It's kind of a lot to keep track of in this question. So first, you want to be able to convert your standard cell notation up here into a reaction, this overall reaction. And in the process of doing that, figure out what your standard cell potential is. And then once you know that, and you have your reaction, you can figure out what Q is, and you'll see that you've already figured out what N is along the way. And so then it's just being organized and putting it all together. Okay, now we have some redox reactions, and they want us to figure out which are going to be positive under standard conditions. And so we know, which are going to be spontaneous, which means they'll have a positive cell potential under standard conditions. And so we're just going to have to figure out what E cell is for each of these. And so for that first reaction, we can split it into the half reactions. So we can see gold solid is becoming gold ions and losing an electron. So it's being oxidized. And so we can find the cell potential for it on the data sheet. But when we look, we'll find instead the reduction of our gold ions. And so we'll have to flip the sign of the reaction. And then you can see we have the reduction of iron as it gains 1 electron to become iron 2+. So here we have to be really careful to make sure we pick the correct iron reduction reaction and make sure we pick the one where we just go from 3+ to 2+. And that has a potential of positive 0.771 volts. And so I'll just add those together to get my standard cell potential. And we can see that's going to be negative. And it is going to be negative 0.919 volts. Okay. And so since it's negative, this is non-spontaneous, and it is out of the running. Okay, and then we're just going to do the same thing for the next reaction. So we can see, again, we have the reduction of iron 3+. This half reaction potential will still be positive 0.771 volts. And then now this is coupled with the oxidation of iodide. As it becomes I2, it gives off 2 electrons. And so we're going to have to look for the reduction of I2 on the data sheet and then flip it. And this is going to be negative 0.536 volts. We can add those together to get our standard cell potential. We can already see it's going to be positive, which is spontaneous, but let's go ahead and figure out the exact number. Ends up being positive 0.235 volts. So that one looks good. It's spontaneous. So let's go ahead and look at our third reaction here. So we can see we have lithium ions becoming solid lithium. That's a reduction. And we can take this half reaction potential straight from the data sheet. And this potential of negative 3.05 volts. And then we can look at the second half of this reaction, which is interesting because it looks like it is also a reduction, right? Because we're taking fluorine gas, which is a 0 oxidation state, to a -1 oxidation state. So it's also gaining electrons. So we can just use this value as is. But the thing is that this isn't really a redox reaction, right? It's just a reaction, which doesn't exist, right? For this to be a true redox reaction, we need something to be reduced, and we need something else to be oxidized. And so since this isn't really a viable redox reaction, it's not going to happen, so we can't call it spontaneous. It's not fair to combine these two reactions in that way, because the standard cell potential is meant to be the reduction half reaction plus the oxidation half reaction. And if we just have reductions, so then the answer for this question is only answer choice B. Okay, here for number 8, Emma is trying to build a battery with a very specific potential of 2.77 volts. And she knows that for whatever reason, she needs to use nickel as one of her electrodes. And so then she's trying to figure out what her other electrode should be. And so I've gone ahead here and written our standard cell potential of 2.77 that we're trying to make. And then here, I have the nickel reduction half reaction written out, and its standard cell potential just from the data sheet. So I know that this standard cell potential is the combination of our half reaction potential for the reduction plus the half reaction potential for the oxidation. So what I'm going to go ahead and do is, use this value for nickel and solve for what the potential for the oxidation would need to be. And so then when I solve, I can see that the oxidation half reaction potential would need to be 3.05 volts positive. And so now I can look on the data sheet and just see if anything has this potential. And what I see is that I do have the reduction of lithium to lithium solid with a potential of negative 3.05 volts. This is a reduction, and I'm looking for the oxidation. So I can go ahead and flip this and flip the potential at the same time, and then I will end up, with the potential that I need in order to make my battery have a standard cell potential. Sorry, the pen's being a little bit silly. A standard cell potential of positive 2.77 volts. Okay, sorry, I'm gonna forgo trying to write out that reaction, but hopefully it's clear that then, by using this, this calculation, we can go ahead and figure out what other components potential would need to be, and then we can match that to the data sheet potentials and see that lithium is the correct answer. Okay, so now for number 9, we have kind of a different type of problem. Here we have a solubility question. And so in this problem, we're given some solution and they tell us it's saturated and that we have this much amount of the barium ions present and this much of the phosphate ions present. And they're trying to get us to figure out what the KSP for that salt would be. And so the KSP reaction always corresponds to taking the solid and dissolving and breaking into the ions in water. And so what these values are telling me when we're saturated is that these are equilibrium values. So if we plug them into our KEQ expression, we'll get our KEQ. And so we can go ahead and set up KSP, which is just a specific type of KEQ. And what we're going to have are aqueous products to the power of their coefficients. Multiplied together. Divided by reactants. And here, our reactant's just a solid, so we'll just call it 1. Boom. And so to figure out our KSP, we're just going to plug in the concentrations from above that we're given. And when we plug this into our calculator and get a number out, that is just going to be our KSP. So you want to be careful when you plug this in to get your order of operations in there carefully. And the number that you get out when you plug this in is 3.45 times 10 negative 23rd, which then matches up about to answer choice C. Here in number 10, we have another solubility problem, but here they give us the KSP. We're not solving for it this time. And what they're trying to get us to figure out is the molar solubility of magnesium hydroxide. The molar solubility is always referring to the X value from our ice table. Then they go ahead and they tell us that our solution is buffered, so we have a pH of 10. Okay, so let's go ahead and just start organizing our thoughts with an ice table. What's nice about the solubility ice tables is we can ignore the solid. And then, they don't tell us anything about the magnesium ions. We can go ahead and say our initial there is 0. But by telling us the pH of the solution, they are telling us something about the hydroxide. And so, what we're going to have to do then is use the pH to figure out our hydroxide concentration. And so what I'm going to go ahead and do is say that 14 minus the pH will give me the POH, and then 10 to the power of my negative POH will give me my concentration of hydroxide. And so in this case, when our pH is 10, we'll just have 10 to the minus 4th, because our POH will be 4, is equal to our hydroxide concentration. So I'm just going to write that here. I'll write it as 1 times 10 to the negative 4th. And it's being buffered so that it stays at this pH. So whatever change we get in our hydroxide concentration from the solid isn't really going to change that overall concentration. And so what I'm going to do is just go ahead and say our hydroxide concentration is going to be constant. It's being buffered to stay the same. But our magnesium, we will get some magnesium. We're going to make 1x because the coefficient on the magnesium is just 1. We'll have an x here for the equilibrium amount. So then we can write our KSP expression, which is just going to be equal to the concentration of magnesium ions times the concentration of hydroxide ions squared. And this was given to us. It's 5.6 times 10 to the negative 12th. And so, just like we have for previous ice tables, we're going to plug in our equilibrium row. And so we'll have x times 1 times 10 to the negative 4th squared equal to 5.6 times 10 to the negative 12th. And when we solve this then, we'll find that x is equal to 5.6 times 10 to the negative 4th. And this is our molar solubility. We'll put it in terms of units of molar. So the answer to this question then is just B. So don't let the hydroxide stuff throw you off too much. Because even if, we did have some change here, our K is so small that we would disregard the added or subtracted change anyway. Okay, so let's go ahead and look at the next question, where we have another sparingly soluble salt, and this is calcium fluoride. And we're trying to figure out how we can make more of it dissolve. And so usually when we're looking at, well, we're looking which would not cause a change. So let's keep that in mind. So in these first two options, we're looking at changing the pH. And the reason that we think about changing the pH as changing the solubility is that if we think about fluoride, we know it's a weak base. So if we added H+ into our solution, we would have this separate equilibrium of it going to become HF. And by having this other route, this path that can kind of suck fluoride out of the solution, we would end up decreasing our products and shifting the reaction to the right. And so changing the pH and changing the amount of protons available for pulling the fluoride into HF will change the solubility of our calcium fluoride. And so for that reason, both A and B would cause a change in our solubility. So those are not going to be the answer because we're looking for what would not change anything. Okay, so then we think about increasing the temperature. And generally, this isn't true for all salts, but generally we do say that increasing temperature increasing the solubility of different solids. Or you can think, changing temperature changes KEQs. And, it will change how much of this dissolves. Whether it's more or less, it's still different. And then we can look at D, adding in more calcium fluoride. And this is a really tempting answer. But if we remember, this is an equilibrium that depends on the presence of aqueous calcium ions and on the presence of aqueous fluoride ions. It doesn't depend on how much of the solid we have around, as long as we have some. So because this is a solid, it's not going to shift our equilibrium at all if we change how much of it there is. Okay, so this would have no effect. So it seems like it would be the right answer. Let's go ahead and look at why E, oops, shoot, my mistake. So let's go ahead and look at why E would cause a change. So let me write that reaction again. Okay, so looking at E, adding in sodium fluoride, we know that sodium fluoride is going to completely dissociate, completely dissolve and dissociate into sodium ions and fluoride ions. So sodium ions don't appear anywhere in the equilibrium that we're interested in, but fluoride ions do. So if we were to add sodium fluoride in, it would be increasing the amount of a product we have. And so it would shift our equilibrium more to left. We'd become less soluble. And so that would change things. And so again, we're left here with D, which is the correct answer, that adding in solid calcium fluoride won't change our solubility. Okay, here we have more solubility questions, but it's written in a little bit of a different way. The idea here is that we have a beaker and it has some silver ions, has lead ions, has calcium ions. And we're trying to think, if we added sodium carbonate, again, sodium isn't going to come into play with solubility, but carbonate will. And we can see that too because here in our equilibrium expressions given for these molecules, there's carbonate in them. But so the idea is we're dropping in carbonate little by little by little. And whichever of these three salts is least soluble will crash out of solution first. And And so what we can do instead is figure out, well, what's the maximum amount of carbonate that can be added at equilibrium? And then the second we would have even just one little bit more, we would start getting a precipitate. And so what I'm going to do is set up 3 ice tables here where we calculate how much carbonate the solutions could tolerate. And then whichever one can handle the least amount of carbonate is going to be the one that precipitates first. So I'm going to go ahead and set up KSP expression for silver carbonate. Dissolving to give us 2 silver ions and 1 carbonate ion. And we can set up an ice table. We're going to ignore the solid. Then we're going to say, okay, I have 0.01 molar of silver ions to begin with, and that just comes from the problem. I'm going to say I haven't added any carbonate in yet. So if I start with 0, what's the max that I can add? And so here our change for the silver would be plus 2x. This would be plus x, 0.01 plus 2x. And then our KSP for this is really small, 8.1 times 10 to the minus 12. And because it's so small, we can ignore any x's that are added or subtracted. I'm just going to go ahead and cross that one out. And so what we'll end up with here is 0.01 squared times x. And so then when I solve for x, I'll be getting the maximum amount of carbonate that I can add before I start getting a precipitate. And I end up getting that it is equal to 8.1 times 10 to the negative 8th molar. Okay, so I'm just going to make a note of that up here. Okay, so now we're just going to do the same thing for the other 2 compounds. Okay, so again, we can ignore the solid in our ice table. We'll put 0.01 here because that's how much we're told we start with. 0 of this, and we can think, okay, I'm adding 1x of that, 1x of this. So we'll have 0.01 plus x and x. We see that our KSP from above is 4.5 times 10 to the minus 9th. And that minus 9th is small enough then that we can ignore any added or subtracted x's. And so then I'll have 0.01 times x as my equilibrium expression when I plug into that KSP. And so this then, x will equal 4.5 times 10 to the minus 7th molar. Okay. So the way I read that is as soon as I have a little bit more than 4.5 times 10 to the minus 7th molar carbonate, I'm going to start to form a precipitate. And so we just compare the silver carbonate to the calcium carbonate. We can see that it takes less carbonate to form the silver carbonate precipitate. And so between these two, so far, we would say that the silver carbonate will precipitate first. It can handle having less carbonate in solution. Now let's go ahead and do the same thing for the lead carbonate. Hopefully you have the rhythm of this down by now. So again, we're not going to include our solid in our ice table. They told us we have 0.1 molar of the lead, so 0.1 there, or 0.01, excuse me. None of the carbonate yet. The change for this will be plus X, plus X. So we will end up with X and 0.01 plus X. Okay, so then we just have to look at our KSP value, which is given to be 7.4 times 10 to the negative 14th. And that's going to be equal to, our aqueous products multiplied together to the power of their coefficients. And it's definitely smallest. It's their smallest KSP, so we can ignore our added or subtracted x's. And so this will end up being 0.01 to the power of 1 times x to the power of 1. That's a multiply, not a plus. Okay. And so then when we solve for x, we will see that it is just equal to 7.4 times 10 to the negative 12 molar. Okay. And so then we can see that the lead carbonate solution would precipitate out first, because as soon as we have this really, really, really small amount of carbonate in solution, we'll end up starting to make a solid. And so this will precipitate out first. Okay. Oh man, here we have some more solubility questions. Cool. Good, good, good. So here I've already set up some ice tables, so that's helpful. But we're just trying to rank these from lowest to highest molar solubility. And so we know molar solubility is the X. Here we're not starting with any amounts. We're not at a given pH to keep track of. So we can just go ahead and do kind of the most basic solubility ice table. So we're going to start with our lead sulfate, ignore the solid. We're not starting with anything. Here we'll just have plus X, X, X. And then we know our KSP is going to be equal to our aqueous products to the power of their coefficients times our aqueous reactants to the power of their coefficients. So we're just going to have X times X. So this is going to be X squared. We can set that equal to the value we were given. And then when we find out what the square root of that KSP is, we will know our molar solubility. And it is going to be 1.58 times 10 to the minus 4 molar. Okay, so now let's do that for our calcium compound. So we're going to ignore the solid again, not starting with anything. Plus X plus 2X, 2X, X. So now our KSP is going to be equal to our aqueous product. So for the calcium, we'll have X. And then for this, we'll have 2x squared. Okay, so you really have to keep track of that 2 kind of in 2 places. And so this does simplify down to 4x cubed. But you really want to keep track of that. Make sure you're squaring the 2 as well as the x. So then we can set this equal to 6.5 times 10 to the minus 6. And so when we solve for x, what I'm going to do is take the KSP, divide it by 4, and then I'm going to have to do the cubed root. And the way that I actually do this is I go ahead and I raise the value to the power of 1/3. So that's the same as doing a cubed root. And so when I solve for this, I get 1.18 times 10 to the minus 2 molar. So make sure you're comfortable doing a cubed root before the exam rolls around. Okay, so finally we have the silver compound. Go ahead and ignore the solid. 0, 0, plus x, x, x. So our KSP is going to be equal just to x from the silver times x with that, x squared. And so then we'll just take the square root to find our molar solubility. And when I do that, I get 2.32 times 10 to the minus 2 molar. And so then we're just going to rank them based on these numbers that I solved for. And so we'll just have 3 greater than 2 greater than 1. And so maybe you're thinking to yourself, hey, Virginia, that seems like kind of a lot of work. Couldn't we have just ranked them based on the KSPs? And the answer is no. You really do need to solve for the x's in the molar solubilities, because as you have different stoichiometries and such, you're not able to just directly compare between the KSPs. But anyway, then we get our answer A. Okay, are you ready to balance a redox reaction? So our first step, assign oxidation numbers. Figure out what's being oxidized, what's being reduced. So this permanganate ion. We don't know anything about manganese. We do know oxygen's preferred oxidation state is -2. We have 4 oxygens. So overall, they're contributing -8. Okay, so this molecule has an overall -1 charge. So that means manganese needs to contribute +7. And there's just 1 manganese. So on its own, it has to contribute +7. Br minus is easy. That's going to have an oxidation number of just 0. Manganese 2 plus is easy. That's just going to be +2. And Br2 on its own, it's just going to be 0. Okay, so then we can look for what's changing. We can see that the manganese and the bromine are changing their oxidation states. So let's go ahead and write the half reactions for those. I have Mn O4 minus becoming Mn2 plus. And I have Br minus becoming Br2. Okay, so looking at our first reaction, we're going from manganese plus 7 to manganese 2 plus. And it's nice because we already have the same number of manganese on both sides of the reaction. And I can see that each one manganese is gaining 5 electrons. That's how it goes from plus 7 to plus 2. I just have 1 manganese, so I'm going to go ahead and add on 5 electrons. So we can tell that this is definitely not balanced though, because we have oxygens on the left and we don't have any oxygens on the right. And so to fix that, I'm going to have to add on 4 waters. So now I have 4 oxygens. But in doing that, I've created a hydrogen problem, a proton problem. So to fix that, now I'm going to have to add protons to the left. We'll have 8 protons added on. Okay, so I think this half reaction's done, but to double check, we can make sure that the charges on the left add up to equal the charges on the right. So charge on the right's easy, that's plus 2. Then over here, I'm going to have minus 5, minus 6, plus 8. It's also going to be plus 2. And so since they match, that's a good sign that that reaction is balanced. Okay. And so now I can look at this bromine reaction. And something that jumps right out at me is that I don't have the same number of bromines. So I'm going to go ahead and put a 2 here. And I can see from my oxidation numbers that each one bromine is losing 1 electron to go from -1 to 0. But here I have 2 bromines. 2 bromines each loses 1 electron. So I'm going to lose 2 electrons. Okay. And now that one's balanced. It's nice we don't have any oxygens that we have to worry about, no hydrogens to keep track of. So this one's done. So our goal is to eventually combine our 2 half reactions into 1 overall reaction. But in order to do that, we need to make sure the electrons cancel out. There's no way for us to just scoop electrons into a reaction. So we can see here they don't match, right? 5 and 2, not the same. And there's no good way really to multiply one of the reactions to make 5 or to divide to make 2. So what I'm going to do is I'm just going to multiply this top reaction by 2 and this bottom reaction by 5. And that way each of them will have 10 electrons overall. So let's go ahead and write what that looks like. Okay, so there's our first half reaction once we've multiplied everything by 2. And then we'll have, for our second half reaction, it's funny, it's like my digital pen runs out of blue ink sometimes. Okay, so we end up then with these 2 half reactions And now we can go ahead and cancel everything, or combine and cancel. So we can cancel our electrons because they're both 10 and they're on opposite sides of the arrow. And what's nice is that since our bottom reaction didn't have any waters or anything, well, we don't have to worry about simplifying down those. So writing this out, we'll have 16H plus. Don't have to worry about the electrons because they've canceled. 2MnO4 minus 10 Br minus 2Mn2 plus 8 waters and 5 Br2s. Okay, so I think we're done, but one way we can check again is to make sure our charges add up to be the same things on both sides of the reaction. So then on the left, we can see we have 16 minus 2 minus 10, so that's going to be 4 plus 4. And then on the right, we can see that we have 2 plus 2's, so that's also going to be 4. So the fact that they match is a really good checkpoint. And so then they're asking us what the coefficient is in front of the bromide ion, and we can see that that's just 10. So boom, E. Okay, so now for number 15, they're asking us which will be more soluble in an acidic solution than if we're just in pure water. And so we find that things that have a basic component in them will be more soluble in acidic solution. And so if we think about, what this would dissociate into, we're going to end up with zinc carbonate breaking into zinc ions and carbonate ions. Not too many, but still some. And so zinc, if anything, is going to be a Lewis acid. It's not basic. But the carbonate ions are definitely a weak base. And so what that means is that if we're in an acidic solution, and if we have extra protons around, then the carbonate could potentially react with the H plus instead of, being in this equilibrium with the zinc. And so if the H plus and the carbonate go off and do their own equilibrium, then that's effectively reducing the amount of carbonate present in solution. It's removing from the carbonate from hanging out with the zinc because it's busy hanging out with the protons. And so that draws the reaction more to the right. That would be an increase in solubility. So anything with a basic component within will be more soluble in acidic solution. So as we can see that would be zinc carbonate. If we looked at bismuth ions and iodide ions, iodide is the what of a what making it a what? Well, iodide is the conjugate of a strong acid making it a negligible base. This is out. The cyanide ions, those are going to be weak base. So they'd be the conjugate of HCN, which is a weak acid. So that's a weak base. It'll be more soluble. And, same thing goes for that zinc sulfide, because you can make H2S. That sulfide is a weak base, so this will be more soluble in acid. And then this is where the tricky part starts. Because HSO4 minus is the conjugate of a strong acid. H2SO4 is strong. And so since it's the conjugate of a strong acid, it's a negligible base. Okay. And so changing the pH, changing or increasing the acidity of the solution won't change the solubility. So the correct answer here is D. Okay, for number 16, we're asked which of the following metals is more easily oxidized than iron. And so what I did is I found iron's least favorable reduction potential and wrote it here, because then its least favorite reduction potential will give us its most favorable oxidation potential, which will just have the opposite sign. And so what we're trying to find is if anything will have a more positive oxidation half reaction potential. And so we're going to use the data sheet. And what we can do is we can look on the data sheet for anything that comes below iron. Because then when we reverse their ions reduction potentials, we'll find that they have a really positive oxidation potential. So if you don't have it beside you, get your data sheet in the oxidation and reduction potential list, and you can find the iron 2+ reduction pretty low on the list. And so what we're going to do is we're going to look on the product side, and we're going to look for the metals below iron on the product side. So right beneath that is chromium. And we can see if we instead wrote the oxidation of chromium, we would have a positive 0.74 volts. And so that would be more favorable, more easily oxidized. And so then, anything below that iron will be more easily oxidized. So chromium, zinc, manganese, aluminum, magnesium, sodium, calcium, lithium. And so then we just have to pick the right one. And so of these, sodium is the one that falls below iron. And that's kind of the idea behind cathodic protection. If we were to coat iron in sodium, which would have its own kind of complications, then the sodium would be oxidized before the iron. Okay, and so this then brings us to the pKa kind of portion of the practice exam. And Todd is actually going to record this part of the video, and he's also going to record the part about the voltaic cell. So look for his content on that. And so with that, good luck. Make sure you're actually doing these problems too. It's really fun to watch me and listen to my soothing Michigan accent, but I think you'll find that it is more beneficial to you if you work through the problems on your own also. So good luck and keep up the hard work. You all are doing great and you can handle this.